Hello everyone, welcome to lecture 50 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on carpet cloaking. So here's the lecture outline. We'll first introduce carpet cloaking, the concept. We'll discuss about the theory and the applications of carpet cloaking. So what is carpet cloaking? So we have always seen in this case that when you do invisibility cloaking, you can actually bend light rays around the object that you are going to hide, and to achieve that you can use transformation optics or transformation electromagnetics that basically does maps the coordinate transformation into the material property. Okay, so what we have seen in the previous lectures, that to achieve some sort of cloaking properties, you require to have the permittivity and permeability both needs to be obtained using metamaterials, and at times the values that are required for those kind of cloaking material are really difficult to achieve. So that is where the carpet cloaking concept will also be very useful and handy, because that will be more practical. So when we talk about a carpet, here we mean it's a reflective surface. Often a bump is created on a reflecting plane, and this bump is basically the carpet under which the object that you want to hide can be placed. So carpet cloaking is basically a practical application of transformation optics. As I mentioned, transformation optics, what it does, it basically uses coordinate transformation that can be mapped into material properties, okay, which are some unusual electromagnetic properties like mu and epsilon, the new values that are required. The carpet cloaking, which is also known as ground plane cloak, is basically a technique that renders an object invisible by making it appear as if it were a part of the flat surface. So effectively it is like hiding it under a carpet. So the concept basically looks very similar, like if you have a kid, or if you have seen any kid hiding his chocolate, okay, he'll just put it under the carpet, right? So the similar kind of concept has been used here, and we will see how it can actually help you achieve the cloaking. So this is basically achieved by manipulating how light or other waves interact with object, causing them to reflect as if it is coming from a flat surface even when an object is present. So the scattering signature of the object is kind of hidden, so you cannot identify the object is there or not. So a carpet cloaking basically aims to conceal an object by making it appear as a flat surface, and this is achieved by altering the path of light or radio waves around the object. So they reflect as if the reflection is coming from flat surface, and where the object is placed, the object is effectively hidden beneath this cloaked surface. Now let us look into the applications of carpet cloaking. As you can understand, the first application would be concealing objects. So this is the most obvious application of cloaking, that you are using a cloaking to hide object from getting detected. They can be used in stealth technology, typically in military applications. This could also involve concealing vehicles or other objects from radar or any other sensor. And then you can also use carpet cloaking for antenna protection. So you can use carpet cloaking to protect antennas, allowing them to transmit or receive signals while remaining undetectable. Okay, and finally you can also use them for making novel lenses, okay, because this kind of carpet cloaks also act as lenses that allows focusing or directing beams of radiation. So transformation optics can be used to design this cloak of invisibility. So the only way to achieve actual transparency would be if the electromagnetic wave coming from behind the object could somehow still arrive with the same trajectory in front of the object as though the electromagnetic waves were transmitted directly through the object. So, here is an illustration of a real life invisibility cloak. We have seen this picture earlier. So, you can see a lady holding a cloaking material in her hand. So, that is allowing the light rays to come around her, so that the view behind her is not blocked. So, in essence, the cloak basically can also make its contents appear very small, and hence that can also render invisible to radars and all. Okay. So, there is another way of doing it, is it's called reshaping an object, and that can be achieved via anisotropic metamaterial coatings. So, how it works, say you have an object which is circular, but you put a anisotropic metamaterial of square shape around it. So, when it is detected by the radar or perceived by the radar, it will be detected as a square object. So, you are basically hiding that particular object. So, there are basically three distinct topological possibilities of cloaking. So, you can either squish an object to a point, okay, or to a line. So, if you do this, in this process of crushing the object, it becomes infinitely conducting, but it is not a problem here because the objects will have very negligible size and they can be rendered invisible. So, that is a good thing. They can become invisible because of their negligible size, but as you can understand, this kind of thing will require extreme and singular values as well as being anisotropic. Okay. The other method could be that you squish an object to a sheet. So, a sheet is highly visible. So, it can be only made invisible if it sits on another conducting sheet, so that they cannot be distinguished, right. So, although you can say that the application here could be more limited, but the invisibility here can be rendered without extreme values and with isotropic material. So, it is more feasible to make this kind of a cloak. So, let us see the theory of carpet cloaking. So, here a cloak to mimic a flat ground plane. Okay. So, basically here you have the physical system. So, you have this object to hide, and then you have this carpet, okay. And then this has to be mapped into a virtual system which looks like a flat ground plane, right. So, this is your virtual system and this is your physical system, and these are the coordinates. Now, carpet cloak does not require singular values for the material parameters. The range for the permittivity and the permeability is much smaller than in the case of a complete cloak. So, you can see the regions in cyan are basically transformed into each other, right. The shaded region basically here represents the ground planes, and the observer perceives the physical system as the virtual system that has got a flat ground plane, but actually there is a object hidden. So, now let us consider the system as the 2D wave problem with electric polarization. So, we can consider the fields to be invariant in the z direction. So, we are only mentioning x and y directions here. So, here you can see a ground plane is basically meaning a highly reflective metal surface that can be regarded as a perfect conductor. Now, you assume that an object lies on that particular plane and a cloak is covered on the object, so that the system is perceived as a flat ground plane again. Okay. So, here is the original or the physical system where you can see the object that has been concealed between the cloak and the original ground plane, whereas the cyan color here is basically showing you cloak, okay, which is typically rectangular of width w and height h, except for the bottom where you need to have that curved shape to leave some enough space for the object to hide. Now this whole configuration is called the physical system with the coordinate x and y, or you can say x1 and x2 in indexed notation. And then this has to be mapped to the virtual system that is shown here. Okay. Now the coordinate here can be labeled as zeta and eta, or you could have named them as zeta 1 and zeta 2. Okay. So this basically shows the width and the height, and here it is a perfect rectangular cloak. Okay. So in general you can see that we are basically considering a coordinate transformation that maps a triangle which is having a width of w and a height of h in the virtual system to an arbitrary region that is the cloak in the physical system, right. So how do you do this coordinate transform? You have to bring back the Jacobian matrix which was discussed earlier. So you can write Aij equals dou xi by dou zeta j. So you are basically going from here to here. Okay. So here zeta 1 and zeta 2 are the basis vectors of the virtual coordinates appearing in the physical system. So from that you can calculate the covariant matrix which is defined as G, and it is calculated as A transpose A. Okay. Now for cloaking, the observer basically perceives the physical system as an isotropic homogeneous medium of permittivity epsilon reference and mu reference. So you take mu reference equals 1, okay, and epsilon reference can be anything. So the corresponding physical system that will be induced by the coordinate transformation will have these values, which is epsilon given as epsilon ref divided by square root of determinant of G, which is the covariant matrix, and then you have the magnetic permeability which is mu. Okay. So that is A transpose divided by square root of determinant of G. So what are this? You can actually see that you have the tangential and longitudinal components of the magnetic permeability. So it is basically represented as the tensor, whereas this is an isotropic value. Okay. So you can write mu t and mu l be the principal values of the permeability tensor in the physical system, right. So you can obtain the corresponding refractive indices as nt, which will be square root of mu l times epsilon, and nl will be square root of mu t times epsilon, right. So these will be the refractive index seen by the two plane waves which are traveling along the two principal axes. Now to indicate the extent of anisotropy in the physical medium, the anisotropy factor, okay, which is also a function of position, can be defined by alpha, which is basically the max of nt by nl or nl by nt. Okay. So if you use the Jacobian matrix Aij, which is dou xi by dou zeta j, and G is basically A transpose A, and then you have obtained this alpha, which is the anisotropy factor. From this you can prove that alpha plus 1 over alpha can be written as trace of G divided by square root of determinant of G. Now trace is basically, for a square matrix, it is basically the sum of the diagonal elements, and if G is a n cross n matrix, then it will be like, trace of G can be calculated as summation over I ranging from 1 to n G I. Okay. So you are again taking the diagonal elements and adding on. Okay. And this is the assumption that mu L times mu T will be equal to 1. So on the other hand, the averaged refractive index n can also be defined relative to the reference medium. So you can get n equals square root of nl n tilde divided by epsilon ref. So that you can obtain this, that n square equals epsilon by epsilon ref, which is nothing but square root of 1 by determinant of G. So now instead of using epsilon and mu ij, okay, that is a permittivity and permeability tensor to describe the physical system, you can now use alpha and n, which have geometrical meaning in terms of the metric. If there is a very fine rectangular grid in the virtual domain with tiny cells of size say delta by delta, such tiny square is basically transformed into parallelogram in the physical domain, because you have to leave that space for the object to hide, okay, and that will have two sides given by zeta 1 delta and zeta 2 delta, okay. A smaller isotropy will mean a smaller value of trace G divided by square root of determinant of G, while a smaller area of the transformed cell, okay, that is square root of determinant of G times delta square, will mean a larger refractive index n, because you know n square can be written as epsilon by epsilon ref, and that is nothing but square root of 1 by determinant of G. So in cloaking, what you will see that the compression of space in the physical domain is essentially making the cloak anisotropic. However, the approach here is to basically minimize the induced anisotropy by choosing a suitable coordinate transformation. If the anisotropy is small enough, we can simply drop it by assigning alpha equals 1 and only keep the refractive index n. So in other words, the physical medium becomes just a dielectric profile described by unit magnetic permeability. So here you can see the transformed grid in physical system with inner cloak boundary, okay. So this is given by this transfinite grid, where the transfinite interpolation is used for a rectangular 40 by 15 grid. So in this case, you can see that the grid is just a linear compression in the y direction, right. So here this color map shows you the value of permittivity, and you can understand that low permittivity is required everywhere, okay. So this medium will be poorly approximated as isotropic because the variation is very less, okay. Now an optimal map can be generated by minimizing the modified Liao function. So you can get a quasi-conformal grid for this particular case, okay. So this is the generated grid using quasi-conformal map, okay, that this kind of mapping can be used, okay. Here what is the catch? Here the grid lines are basically orthogonal. So the aspect ratio of each cell of this particular case, or you can say the anisotropic factor alpha, basically becomes a constant of 1.042, okay, while you can see that n square in this case is basically ranging from 0.68, that is typically the dark blue value, to almost 1.96, okay. So here n or epsilon stays finite without approaching either 0 or infinity. So the singular values are avoided. So it is basically a result of crushing the object to a plane instead of crushing it to a line or a point. So you are getting values which are easily achievable, right. So no singular points basically occur in this kind of coordinate transform, right. But what you can see that there are some high permittivity. So in this case the medium is well approximated as isotropic, okay. I think that's a typo here, it should be anisotropic, yeah. So now let us see how it is working. So to test the effectiveness of the designed cloak, suppose that you have made a cloak which is 4 micron by 1.5 micron, okay, and the cloak is basically defined relative to silica, which has got a epsilon reference of 2.25, okay. So what we will do, we employ the quasi-conformal grid that you have seen earlier, but ignore the anisotropy in the cloak by only keeping the epsilon profile with unit permeability. So, you are keeping mu equals 1. So, in this case the permittivity of the cloak will vary from say 1.5 to 4.4 typically, okay, and this range can be obtained easily by effectively etching or drilling sub-wavelength holes of different size along the z direction in a high dielectric material such as silicon. So, it becomes more achievable. Now, outside the cloak you can again see that the silica is working as the background material. Moreover, the inner surface of the cloak is coated with highly reflective metal. So, to the observer it is perceived as if this is the actual ground plane, and this is relevant to the situation of routing light at our own will in the optical integrated circuits. So, this is a clear picture that shows that what happens with a carpet cloaking and without a carpet cloaking. Okay. So, these are nothing but the electric field patterns with the cloak located within the rectangle, as you can see here. This is the dashed line is the boundary, okay, and this is where the bump is, where the object is hidden, and then on top of that you have put the cloak. Okay. So, this is basically the physical cloak that you have seen earlier, right. So, we are basically considering Gaussian beam which is launched at a 45-degree angle towards the ground plane from the left, okay, and the width of the beam is around 4 micron at a vacuum wavelength of 750 nanometer, and we considered silica as the background. So, if you compare this with this, the electric field pattern when only object, or you can say a reflecting surface of shape of the inner cloak boundary is present without the cloak. So, you can see that this is how the scattering will tell you that there is an object over here, but as soon as you put the cloak, it is getting reflected only in one direction as if it is reflected from a flat ground plane. So, this is how the cloaking works. The other applications of carpet cloaking, as we briefly mentioned, would be to reshape the scattering of the objects. So, that way also it will be able to disguise one object in another form, right. So, the electric field contours in finite element simulations for reshaping a rectangular object into an elliptical object is shown here. So, this is the object to be perceived, and the equivalent problem via anisotropic metamaterial layer can be seen here. So, this particular diagram shows you that what is the scattering profile from an elliptical object. Now, here what is happening, you have basically put that elliptical object into this kind of a cloaked medium. Okay. So, you are basically getting the scattering from a rectangular object which is embedded in an anisotropic medium designed by this transformation optics, and this overall thing basically scatters just like an elliptical object. So, what is happening, you are basically able to hide your object which is rectangular in shape, because it will give its identification as a elliptical object. So, that is called reshaping the scattering from objects. You can also see another example where the electric field contours in finite element simulation shows reshaping of a square PEC object into a dielectric object. Okay. So, this is the object to be perceived, okay, and this is the equivalent problem via an anisotropic metamaterial layer. So, you can see that you are reshaping for a square PEC into a dielectric object. So, you are basically giving it the scattering property of a different material. So, you can put any dielectric object, okay, and you can see that this kind of scattering signature will be obtained when you put a cloak around it, right. So, this is how carpet cloaking can help you first hide an object on a ground plane, or you can also reshape the scattering from any object as if the scattering is coming from a different shape objects. So, these are the two vital applications of carpet cloaking. So, with that we will conclude here. We will look into the transformational electromagnetics for antenna applications and stealth technology in the next lecture. If you have got any query regarding this lecture, you can drop an email to this email address mentioning the course title and the lecture number on the subject line. Thank you.